August 17, 1943. 18,000 feet over the Solomon Islands. Lieutenant Richard Bong watched his wingman's P-38 Lightning spiral into the Pacific below. 3 Japanese Zeros had bounced them from above. Now Bong was alone. The lead Zero closed on his tail. He had perhaps 4 seconds before 20mm cannon fire tore through his aircraft. What happened next wasn't in any training manual. Bong rolled his P-38 completely inverted and yanked the stick forward. Instead of climbing away from the threat, his aircraft dove toward the ocean. But because he was upside down, he pulled away in a direction the Zero pilot never anticipated. Blood rushed to his head. His vision went red at the edges. The Pacific Ocean filled his canopy where the sky should have been. The Zero pilot, expecting Bong to climb, overshot. In those 3 seconds of confusion, Bong rolled upright below the Zero and pulled up hard. His .850 caliber machine guns raked the Zero's belly from a position no Japanese pilot had ever encountered. An American fighter attacking from below. The Zero disintegrated. By August 1943, American pilots in the Pacific faced a brutal reality. The Zero could outturn any American fighter. Japanese pilots exploited this advantage ruthlessly. Standard doctrine called for American fighters to use their superior speed and firepower. Dive, shoot, climb away. Never turn with a Zero. The numbers told a grim story. In the first year of Pacific air combat, the Zero maintained a kill ratio of nearly 3-to-1 against American fighters. The A6M Zero could turn inside a circle roughly 400 feet tighter than a P-38 at combat speeds. When an American pilot tried to dogfight, the Zero simply turned harder and positioned for the kill. Lieutenant Colonel Thomas Lynch documented the problem in his August 1943 after-action report. Our pilots maintain speed advantage but cannot engage in sustained combat. The moment we slow down or turn, the Zero has us. We trade 1 kill for every 3 losses in turning fights. The P-38 Lightning brought advantages. Twin Allison engines producing 2,600 horsepower combined, top speed of 414 miles per hour, .850 caliber machine guns, and 120mm cannon concentrated in the nose. A P-38 pilot who kept his speed could devastate Zeros in a single pass. But combat rarely allowed perfect conditions. Japanese pilots had been fighting since the late 1930s over China. They understood energy management at an expert level. They knew exactly how to force American pilots into situations where the Zero's turning ability became decisive. A common Japanese tactic involved 1 Zero acting as bait, flying straight and level, appearing vulnerable. When an American pilot committed to the attack, 2 more Zeros would drop from above, or slide in from the flanks. The American fighter was suddenly defensive, and defensive meant entering a turning fight, which meant the Zero's advantages became overwhelming. What Bong stumbled onto that day over the Solomon Islands was something aviation medicine considered impossible. The maneuver involved rolling inverted and pulling through into a diving turn. In normal flight, pilots experience positive G-forces. Blood is pushed toward their feet. Vision narrows. At around 5 to 6 Gs, many pilots experience grayout or blackout. But when a pilot rolls upside down and pulls the stick forward, he experiences negative Gs. Blood rushes to the head. The effect is called redout, because the visual field literally turns red as blood vessels in the eyes engorge. Aviation medicine in 1942 suggested humans could barely tolerate negative G-forces. Studies indicated that even -2 Gs caused severe discomfort, disorientation, and potential retinal damage. Official guidance recommended avoiding negative G flight entirely. But these studies were conducted in controlled environments, with test pilots who weren't being shot at. Combat created different mathematics. A pilot experiencing 2 seconds of readout vision but escaping a Zero's gun solution survived. A pilot who maintained perfect positive G flight but stayed in the Zero's crosshairs died. The choice wasn't comfortable versus uncomfortable. It was temporary blindness versus permanent death. The physics behind why the inverted dive worked involved energy management and opponent prediction. When a Zero pilot achieved a tail position, he anticipated the target would either try to outturn him, which was impossible, or attempt to climb away, which bled the American aircraft's energy and made it an easier target. The inverted dive did neither. It converted altitude into speed in a vector the Zero pilot didn't expect. More importantly, if the Japanese pilot attempted to follow through the maneuver, his aircraft faced structural limitations. The Zero was stressed for positive G loads up to about 7 Gs, but its lighter construction made negative G flight particularly dangerous. Pulling negative Gs in a Zero risked structural failure or engine problems because the aircraft's systems weren't designed for sustained inverted flight. The P-38's twin Allison engines had another advantage in negative G flight. Unlike single-engine fighters with carbureted engines which could experience fuel starvation during inverted maneuvers, the P-38's engines used different fuel systems that functioned more reliably under negative G loads. This wasn't a design feature. Lockheed engineers weren't planning for inverted combat tactics, but it became operationally significant. A P-38 pilot could maintain power through an inverted dive while some pursuing aircraft might experience momentary power loss, widening the separation. The human body's tolerance for negative G-forces turned out to be higher than medical literature suggested, provided the exposure was brief. Pilots reported that the redoubt effect lasted only a few seconds during a properly executed split S maneuver. Vision returned as the aircraft transitioned back to positive G flight during the pullout. The discomfort was intense. Headaches, facial petechiae, bloodshot eyes, but survivable. Several pilots noted in debriefings that they'd rather endure a splitting headache back at base than a proper burial at sea. The informal risk assessment was simple. Negative G maneuvers hurt, but Japanese cannons hurt worse. Major Thomas Lynch of the 39th Fighter Squadron, flying P-38 Lightnings out of Port Moresby, New Guinea, was the first pilot documented to have used the inverted dive tactic deliberately rather than instinctively. On April 11, 1943, Lynch led a 4-plane patrol over the Huon Gulf when his formation encountered 8 Zeros at 20,000 feet. Instead of engaging in a traditional horizontal fight, Lynch immediately rolled inverted when the lead Zero closed on him. He pulled through into a steep dive, accelerated to over 400 miles per hour, then rolled level at 8,000 feet. The Zero pilot, attempting to follow, pulled out at 12,000 feet, either unwilling or unable to match Lynch's dive angle and speed. Lynch didn't just survive the encounter, he reversed the situation. After leveling out, he had both altitude separation and superior speed. He used that energy advantage to climb back up, this time approaching the now disorganized Japanese formation from below. The Zeros had lost their cohesion, chasing after what they thought were fleeing American fighters. Lynch shot down 2 Zeros in the ensuing engagement. His wingmen, following his example through the inverted dive, survived without losses. The after-action report noted the tactic but didn't emphasize it. Official doctrine still discouraged negative G maneuvers. What made Lynch's action significant was intentionality. Other pilots had rolled inverted under duress, survived, and chalked it up to luck. Lynch recognized it as a repeatable technique. Within a week, he was teaching the maneuver to other pilots in his squadron during informal briefings. The instruction was simple. If a Zero gets on your tail in a position where you can't shake him conventionally, roll inverted, pull through, dive hard, and use the speed to separate. Don't try to outturn him horizontally. Use the vertical dimension. The Zero owns the horizontal circle, but American fighters owned the vertical dive. By June 1943, the tactic had spread to other P-38 units operating out of Guadalcanal and the Russell Islands. Pilots shared the technique during ready room discussions and inter-squadron debriefings. It remained largely unofficial. Not prohibited, but not endorsed in formal tactical directives either. Squadron leaders recognized its effectiveness, but hesitated to put it in writing. The concern was partly liability. If a pilot was killed attempting the maneuver, questions would arise about who authorized teaching a tactic that contradicted established training. So it spread through word of mouth. Experienced pilots showing newer arrivals how to execute it without documenting the instruction. Flight Surgeon Captain James Moorhead, stationed at Henderson Field on Guadalcanal, began documenting the physical effects of negative G maneuvers in July 1943. His medical reports, which remained classified until 1947, provided the first systematic analysis of what pilots were actually experiencing. Moorhead examined 17 pilots who had executed inverted dives during combat between May and August 1943. Every pilot reported the same visual phenomenon. Vision went red within 1 to 2 seconds of pulling negative Gs. The redness started at the periphery and moved inward. For most pilots, central vision remained functional for 3 to 5 seconds during the maneuver, enough time to maintain aircraft control and execute the escape. After landing, pilots exhibited predictable physical symptoms. Petechiae, tiny red dots caused by broken capillaries, appeared on their faces, particularly around the eyes and across the forehead. Severe headaches lasting several hours. Bloodshot eyes from increased ocular pressure. One pilot reported temporary double vision that resolved after approximately 6 hours. Moorhead's most significant finding was that repeated exposure didn't cause cumulative damage. Pilots who executed the maneuver multiple times showed the same symptoms each time, but no worsening effects. The human cardiovascular system adapted to brief negative G exposure better than medical theory predicted. The key word was brief. Sustained negative G flight of more than 10 seconds did cause more serious problems, including potential retinal detachment. But combat maneuvers rarely required more than 3 to 5 seconds of inverted flight. The medical data provided unofficial validation for what pilots already knew from experience. The maneuver hurt, but it wouldn't kill them. Japanese cannon fire would. By September 1943, the inverted dive had become standard procedure in several P-38 squadrons, though still not officially documented in training materials. The tactical situation in the Pacific was changing. American production had begun overwhelming Japanese numbers. More P-38s arrived monthly. Pilot training improved. The Zeros, which had seemed invincible in 1942, now faced opponents who understood their strengths and limitations. Japanese pilots noticed the change. Saburo Sakai, one of Japan's highest-scoring aces, wrote in his post-war memoir about encountering American pilots who used vertical maneuvers that seemed suicidal, but proved effective. The Lightning pilots stopped trying to turn with us. Instead, they would roll inverted and dive away at speeds we could not match. When we pursued, they would reverse and attack from below, a position we never expected. The psychological impact was significant. Zero pilots had dominated the Pacific Air War through superior turning ability. American pilots who refused to engage in turning fights negated that advantage. The inverted dive was particularly frustrating because it converted what should have been a kill position into a neutral situation, or worse, reversed the advantage entirely. Lieutenant Robert Westbrook of the 475th Fighter Group recorded an engagement on November 8, 1943 that demonstrated the tactic's effectiveness. His 4-plane P-38 patrol encountered 9 Zeros over Rabaul at 14,000 feet. The Zeros had the altitude advantage and dove on the American formation. Instead of breaking left or right into a horizontal turn, all 4 P-38 pilots rolled inverted simultaneously and pulled through into steep dives. The Zero formation, expecting a turning fight, overshot. The P-38s accelerated to over 420 miles per hour in the dive, opening separation from the Zeros. At 6,000 feet, the American pilots pulled out, reformed, and climbed back into the fight with both speed and positional advantage. The Zeros, now at lower altitude and having burned energy in their initial attack, couldn't regain advantage. Westbrook's flight shot down 3 Zeros without losses. His after-action report specifically credited the inverted dive with preventing what would have been a disadvantageous engagement. The tactic's effectiveness came from exploiting multiple factors simultaneously: speed separation, altitude conversion, opponent disorientation, engine reliability under negative G loads, and perhaps most importantly, pilot willingness to endure temporary physical discomfort for tactical advantage. That last factor proved decisive. American pilots learned they could tolerate the readout effect. Japanese pilots found that their aircraft handled poorly under negative G loads, discouraging pursuit through inverted maneuvers. By early 1944, the tactical balance in the Pacific had shifted dramatically. P-38 squadrons using vertical fighting tactics achieved kill ratios that reversed the earlier Japanese advantage. The 475th Fighter Group, which fully adopted the inverted dive technique by December 1943, recorded a kill ratio of 5-to-1 in their favor over the first quarter of 1944. Other squadrons reported similar improvements. The 5th Air Force in the Southwest Pacific began incorporating vertical maneuvers into official tactical guidance in March 1944, nearly a year after pilots had started using them in combat. The delay reflected institutional caution about endorsing techniques that contradicted established doctrine and medical advice, but combat results made the case undeniable. Training materials began including sections on negative G flight, though the language remained cautious. Pilots were instructed that inverted maneuvers should be used only when facing imminent threat with no other escape option. The guidance emphasized brief duration, proper technique, and awareness of physical effects. It was permission without encouragement. Use this if you must, but we're not recommending it. Pilots interpreted the guidance differently. If the tactic worked and command wouldn't prohibit it, that was authorization enough. By mid-1944, every P-38 pilot in the Pacific knew how to execute an inverted dive. Many practiced the maneuver during training flights, despite official discouragement, because they understood that the first time executing it shouldn't be with a 0 on their tail. The physiological research continued. Flight surgeons documented that pilots could build tolerance to negative G forces through repeated exposure. Similar to positive G tolerance training, the body adapted. Blood vessel walls strengthened. Visual recovery time shortened with experience. Pilots who had executed 20 or more inverted dives reported less severe symptoms than those performing it for the first or second time. This created an experience advantage. Veteran pilots handled the maneuver more effectively than new arrivals. It became another skill that separated effective fighter pilots from those who didn't survive long enough to gain experience. Squadrons began informal mentoring, where experienced pilots would take new arrivals up and demonstrate the technique in controlled conditions before they needed it in combat. The inverted dive wasn't just a maneuver. It became part of P-38 fighting culture in the Pacific, a shared experience that connected pilots across squadrons. When pilots from different units met, they'd compare notes about their worst readout, their fastest dive speed, or the time the tactic saved their life. It created esprit de corps, built around tactical competence and shared suffering. Japanese pilots adapted, eventually. By late 1944, experienced Zero pilots learned not to follow P-38s through vertical maneuvers. They would break off pursuit when American fighters rolled inverted, knowing that attempting to follow was futile and potentially dangerous. This adaptation meant the tactic remained effective even after opponents understood it, because it still achieved its primary purpose: breaking contact and preventing the Zero from establishing a kill position. The evolution continued through the war's end. Pilots experimented with variations. Some used a half roll before pulling through, which reduced negative G exposure but required more altitude. Others combined the inverted dive with a barrel roll during the pullout, creating an unpredictable flight path. The basic technique spawned dozens of tactical refinements as pilots adapted it to different situations. By war's end, the inverted dive and related vertical maneuvers had become fundamental to American fighter tactics in the Pacific. The technique's legacy extended beyond World War II. During the Korean War from 1950 to 1953, American jet pilots rediscovered the principles their predecessors had developed over the Pacific. F-86 Sabre pilots facing Soviet-built MiG-15s found themselves in a situation similar to what P-38 pilots had experienced against Zeros. The MiG-15 could outturn the F-86 at most altitudes. Soviet and Chinese pilots exploited this advantage effectively. Captain Joseph McConnell, who became the top American ace of the Korean War with 16 confirmed kills, explicitly credited vertical fighting tactics learned from World War II veterans. In his debriefings, McConnell described using negative G dives to escape MiG attacks when caught in disadvantageous positions. The physics hadn't changed. The MiG pilot expected horizontal maneuvering. Rolling inverted and diving created separation and confusion. The jet era brought new complications. Jet engines of the 1950s sometimes experienced flameout during negative G flight, as fuel delivery systems struggled with inverted operation. F-86 pilots learned to keep their maneuvers brief, not just for physiological reasons, but for engine reliability. A 3 to 5 second inverted dive worked. Longer duration risked engine failure. Modern aviation medicine has extensively studied negative G forces since those early World War II observations. Research conducted by the United States Air Force School of Aerospace Medicine beginning in the 1960s confirmed what Richard Bong and his contemporaries discovered through necessity. Humans can tolerate brief negative G exposure of -2 to -3 Gs with minimal long-term effects. The visual phenomenon pilots called readout occurs because blood pressure in the cranial blood vessels increases dramatically under negative G loads. The small blood vessels in the eyes engorge, creating the characteristic red visual field. Recovery is rapid once positive G flight resumes. Modern understanding shows that permanent damage requires either very high negative G forces, above -5 Gs, or sustained exposure lasting more than 15 seconds. Combat maneuvers rarely approach those extremes. Fighter aircraft design evolved to accommodate negative G capabilities. The F-16 Fighting Falcon, introduced in the mid-1970s, incorporated fuel systems specifically designed to operate under negative G conditions. The aircraft's fly-by-wire flight control system allowed sustained inverted flight without the engine problems that plagued earlier jets. Negative G maneuvers became an expected part of the F-16's performance envelope rather than an emergency technique. At the Navy Fighter Weapons School, commonly known as Top Gun, instructors teach negative G tactical maneuvers as standard curriculum. The program, established in 1969 partly because American pilots in Vietnam struggled against more maneuverable MiG fighters, incorporates lessons learned across 5 decades of air combat. One of those lessons traces directions directly back to Richard Bong over the Solomon Islands in 1943. When your opponent has a turning advantage, use the vertical dimension. Modern fighter pilots train with specialized equipment that helps them understand their physiological responses to negative G flight. Centrifuge training exposes pilots to sustained negative G forces in controlled conditions, allowing them to recognize the symptoms and learn their personal tolerance limits. The visual effects, discomfort, and recovery times are documented and explained as normal responses rather than indications of system failure. The F-22 Raptor and F-35 Lightning II, America's most advanced fighters, both incorporate thrust vectoring and advanced flight control systems that allow sustained high negative G maneuvers. These aircraft can maintain -3 to -4 Gs for extended periods without engine problems or control complications. What Richard Bong achieved through desperate improvisation is now a programmed capability in fifth-generation fighters. The basic human factors haven't changed. Pilots still experience redoubt. Blood still rushes to the head. The discomfort remains. But modern pilots understand the phenomenon, train for it, and know it doesn't indicate danger. That psychological shift, from viewing negative G flight as potentially fatal to seeing it as merely uncomfortable, represents a fundamental change in fighter tactics. The spread of this tactical knowledge illustrates how combat innovation occurs. Official doctrine and engineering typically lag behind what pilots discovered through necessity. Richard Bong didn't consult medical literature or engineering specifications. He rolled inverted because dying seemed worse than temporary blindness. That calculation, repeated by thousands of pilots over decades, gradually changed fighter tactics worldwide. The inverted dive and related negative G maneuvers remain relevant in modern air combat despite technological advances. Contemporary air-to-air missiles have excellent tracking capabilities, but they still require positioning and timing. A fighter executing a sudden negative G maneuver creates tracking problems for both missile guidance systems and pursuing aircraft. The unexpected vector change forces the enemy to recalculate intercept solutions, buying valuable seconds. During Operation Desert Storm in 1991, coalition pilots reported using -G brakes to evade Iraqi surface-to-air missiles and air-to-air threats. The tactic's effectiveness persisted even against more advanced weapon systems. Physics and human reaction time don't change with technology. An opponent expects certain maneuvers based on common tactical doctrine. When a pilot does something outside that expectation, it creates decision paralysis, even if only for a few seconds. Those seconds matter. In air combat, a 2-second advantage in positioning can determine survival. Richard Bong understood that in 1943. Modern pilots with heads-up displays, helmet-mounted sights, and beyond visual range missiles face the same fundamental equation. Survive the next few seconds, then use that survival to reverse the situation. The medical research continues. Studies conducted through the 2010s examined how modern G-suits and flight equipment affect -G tolerance. Standard G-suits, designed to prevent blood from pooling in the legs during positive G maneuvers, don't help much during -G flight. Some experimental systems attempted to restrict blood flow to the head during inverted flight, but pilot acceptance was poor. The equipment added complexity without providing benefits proportional to the additional weight and discomfort. Modern pilot training emphasizes that -G maneuvers are tools in the tactical toolkit, not emergency-only techniques. New fighter pilots learn inverted flight during basic flight training, long before they encounter combat situations. This represents a complete reversal from the World War II era, when pilots discovered the technique independently and training materials discouraged it. The shift reflects broader changes in how military aviation approaches innovation. The modern process includes structured testing, medical research, and official incorporation of new tactics into training programs. But combat still produces innovations faster than institutional processes can validate them. Iraq and Afghanistan saw pilots develop new tactics for close air support and urban combat that weren't in any manual, but proved effective in actual operations. The pattern repeats. Pilots facing life-or-death situations innovate. Survivors share what worked. Eventually, the innovation becomes doctrine. This cycle, from desperate improvisation to standard procedure, characterized how the inverted dive evolved from Richard Bong's split-second decision over the Solomon Islands to a fundamental element of modern fighter tactics. Richard Bong finished the war as America's top-scoring ace with 40 confirmed victories. He survived the Pacific Air War and returned to the United States in 1945. On August 6, 1945, the same day the atomic bomb fell on Hiroshima, Bong was killed test flying a P-38 Shooting Star jet fighter. Engine failure during takeoff. He was 24 years old. The irony wasn't lost on those who knew him. Bong had survived hundreds of combat missions, pioneered tactics that saved countless pilots, and faced Japanese fighters across 2 years of intense combat. He died testing a new aircraft in relatively safe conditions. Combat veterans understood. Flying was inherently dangerous whether facing enemy fire or not. The risks never truly disappeared. Major Thomas Lynch, who documented and systematized the inverted dive technique, didn't survive the war either. He was shot down over Taji, New Guinea on March 8, 1944, becoming one of over 33,000 American aircrew killed in the Pacific Theater. His tactical innovations outlived him by decades, incorporated into training programs and fighter doctrine without most students knowing his name. The pilots who developed these techniques rarely received credit in official histories. No medals were awarded for inventing new maneuvers. The Medal of Honor went to pilots who shot down multiple enemies in single engagements, not to those who figured out better ways to escape when outnumbered. But among pilots themselves, the tactical innovators held special status. They were the ones who found solutions that kept people alive. Flight surgeon James Moorhead continued his medical research after the war, eventually becoming one of the leading experts in aviation medicine. His classified wartime reports on -G physiology provided the foundation for decades of subsequent research. When the Air Force established formal aerospace medicine programs in the 1950s, Moorhead's data informed the training protocols and safety standards. The broader tactical lesson from -G maneuvers extended beyond specific aircraft or historical periods. Combat forces innovation in ways that peacetime training cannot replicate. The pressure of actual life-or-death decisions compresses learning timelines. What might take years to develop through systematic research and testing can emerge in weeks when pilots face it operationally. Military institutions struggle with this dynamic. Official doctrine requires validation through testing, safety analysis, and institutional approval. This process exists for good reasons. Untested tactics can get people killed as easily as effective tactics save them. But combat doesn't wait for official approval. Pilots improvise, and effective improvisations spread through informal networks faster than formal institutions can evaluate them. The inverted dive illustrated this tension perfectly. By all official measures in 1942 and early 1943, the maneuver should have been prohibited. Medical guidance suggested it was dangerous. No training program taught it. Engineering specifications for most aircraft didn't validate it. Yet pilots used it anyway, because the alternative was worse. This created a command dilemma. Squadron leaders and higher headquarters knew pilots were using the technique. They saw the survival rates improve. But officially endorsing something that contradicted established safety guidance created liability issues. The compromise was tactical ambiguity. Don't prohibit it, don't endorse it. Document the results, and let the medical and engineering staffs catch up with operational reality. By 1944, enough data existed to change official positions. The medical research showed the technique was survivable. Engineering tests confirmed that properly maintained aircraft could handle the stresses. Training programs began incorporating it, though cautiously. The institutional processes eventually validated what pilots had proven in combat a year earlier. Modern military organizations try to shorten that validation cycle. After-action reporting systems, rapid assessment protocols, and flexible training programs attempt to capture and disseminate tactical innovations faster. But the fundamental tension remains. Combat generates innovation faster than institutions can officially incorporate it. The inverted dive also demonstrated how tactical knowledge transfers across generations of pilots. The technique developed in World War II against Zeros influenced Korean War pilots facing MiGs, which informed Vietnam War tactics, which shaped training for Gulf War operations, which affected how contemporary pilots think about air combat maneuvering. Each generation refined the technique, adapted it to new aircraft and situations, and passed it forward. This continuity exists despite massive changes in technology. World War II pilots flew propeller-driven aircraft with mechanical controls. Modern pilots fly jets with computer-managed flight systems. But the underlying principles of energy management, opponent psychology, and physiological tolerance remain constant. A pilot from 1943 transported to 2024 would need extensive training on the equipment, but the tactical concepts would be immediately recognizable. Institutional memory preserves this knowledge. Fighter squadrons maintain traditions and unofficial histories that capture lessons beyond what appears in official documentation. When a new pilot joins a squadron, experienced pilots share stories about tactics that worked, pilots who innovated effectively, and situations where unconventional thinking saved lives. The inverted dive features in those stories, directly or indirectly, as an example of effective tactical innovation. The technique also illustrates human adaptability under stress. The physical effects of negative G-flight are intensely uncomfortable. Headaches, visual distortion, nausea, disorientation. Every physiological signal tells the pilot this is wrong, dangerous, to be avoided. Yet thousands of pilots learned to ignore those signals because they understood the larger context. Temporary discomfort beats permanent death. That calculus requires a specific mental framework. It's not courage in the traditional sense. It's more analytical. Assessment of relative risks. Understanding that the body's warning systems evolve for different threats than high-speed aerial combat. Recognition that survival sometimes requires accepting short-term suffering to avoid long-term consequences. Modern fighter pilot training explicitly develops this mindset. Pilots learn that their instincts will sometimes be wrong in aerial combat. The natural response to seeing the ground rushing up is to pull back, climb away. But in certain situations, diving toward the ground creates escape opportunities. Training builds cognitive frameworks that allow pilots to override instinct when tactical analysis indicates a different action. This represents sophisticated decision-making under extreme stress. In the seconds available during air combat, pilots must assess the tactical situation, evaluate options, predict opponent responses, calculate relative risks, and execute maneuvers that may contradict instinct. The pilots who survive develop this capability. Those who don't rarely get a second chance to learn. The inverted dive became one element in a larger tactical repertoire. Effective fighter pilots mastered dozens of maneuvers, each applicable in specific circumstances. They learned to recognize which situation called for which response, often at speeds where conscious deliberation wasn't possible. The knowledge had to become almost automatic. See this threat pattern? Execute that maneuver sequence. Adjust based on result. Building that automatic response requires extensive training and experience. Pilots in World War II typically needed 15 to 20 combat missions before their tactical decision-making became reliable. Modern pilots spend hundreds of hours in simulators and training aircraft before their first combat deployment, attempting to compress that learning curve. But combat still teaches lessons that simulation cannot fully replicate. The emotional stakes drive different learning. In training, mistakes mean embarrassment, negative evaluations, or, at worst, minor injuries. In combat, mistakes mean death. That reality focuses attention powerfully. Pilots remember combat lessons with a clarity that training lessons rarely achieve. The memory of executing an inverted dive with a 0 on the tail, feeling the redoubt effects, seeing the maneuver work, reinforces the technique far more effectively than any classroom instruction. Post-traumatic learning is real and powerful. Pilots who survived by using the inverted dive didn't need refresher training on the technique. The combination of fear, physical sensation, and successful outcome created indelible neural pathways. They could execute the maneuver years later with the same precision they demonstrated during that first desperate combat execution. This has implications for how fighter tactics develop. The most effective techniques often emerge from maximum stress situations where pilots had no time for detailed analysis. They acted on instinct, training, and immediate tactical assessment. When those actions succeeded, the success reinforced the behavior pattern. Other pilots observed or heard about it, tried it themselves, and either confirmed it worked or discovered its limitations. The decentralized evolution of tactics through this process creates robustness. No single theorist or test pilot determined that inverted dives were effective against zeros. Dozens of pilots independently discovered it worked. The technique survived and spread because it demonstrated effectiveness across varied conditions and situations. Natural selection in the most direct sense. Tactics that worked proliferated. Tactics that didn't got pilots killed and disappeared from the repertoire. Modern military organizations try to systematize this evolutionary process through structured experimentation and operational testing. Red flag exercises, training centers that replicate combat conditions, and after-action review systems all attempt to create environments where tactical innovation can emerge and be evaluated without actual combat. These systems work reasonably well. They've shortened the development cycle for new tactics considerably compared to historical patterns. But combat still produces surprises. Operations in Iraq and Afghanistan generated tactical adaptations that weren't predicted by training or doctrine. Close air support in urban environments, counter-IED operations, and integration of unmanned systems all required tactical innovations that emerged from operational necessity. The pattern holds. Combat demands solutions. Operators improvise. Effective improvisations spread. Eventually, institutions incorporate them into doctrine. The inverted dive occupies a special place in this history because it represents one of the earliest systematically documented examples of combat-driven tactical innovation. The World War II military, particularly the Army Air Forces, developed relatively sophisticated systems for capturing and disseminating tactical lessons. After-action reports, technical bulletins, and training updates spread information across theaters faster than in previous wars. This allowed the inverted dive technique to proliferate through Pacific Theater P-38 squadrons within months of its initial development. European theater pilots facing different opponents in different aircraft didn't adopt it as widely because the tactical situations differed. But the principle of vertical maneuvering to exploit aircraft performance advantages did transfer. Pilots facing FW-190s or ME-109s learned their own versions of using dive performance to escape disadvantageous situations. The technological convergence between different fighter generations shows how fundamental principles persist, even as equipment changes dramatically. A P-38 pilot from 1943 and an F-35 pilot from 2024 fly aircraft separated by 8 decades of technological development. Yet both understand that when facing an opponent with superior turning performance, vertical maneuvers provide escape options that horizontal maneuvering cannot. This knowledge transfer happens through multiple channels. Official training programs teach the techniques explicitly. Informal mentoring passes tactical wisdom from experienced to new pilots. Historical study provides context for why certain tactics developed and how they evolved. Together, these create institutional knowledge that survives personnel turnover and technology transitions. The Vietnam War provided another crucible for negative G tactics. American F-4 Phantom pilots faced North Vietnamese MiG-17s and MiG-21s that could outturn them in specific flight regimes. The F-4 was designed primarily as a missile platform, optimized for beyond visual range engagements. When forced into close-range dogfights, its size and weight created disadvantages against smaller, more maneuverable opponents. Navy Lieutenant Randy Cunningham, who became the first American ace of the Vietnam War with 5 confirmed kills, explicitly used vertical maneuvers, including negative G brakes, to escape disadvantageous situations against MiGs. In his engagement on May 10, 1972, where he shot down 3 MiG-17s in a single mission, Cunningham executed an inverted dive to separate from a MiG that had achieved a brief tail position. The tactic worked for the same reasons it worked against Zeros 30 years earlier. The MiG pilot expected horizontal maneuvering. The sudden vertical displacement created separation and confusion. Cunningham used that separation to reverse the situation and re-engage from advantage. The physics hadn't changed. The opponent's psychology hadn't changed. The effectiveness persisted. Vietnam also demonstrated how institutional knowledge can be lost and rediscovered. By the mid-1960s, many of the World War II and Korean War veterans who understood close-range aerial combat tactics had retired. Younger pilots trained in an era emphasizing missiles and radar-guided engagements. When forced into visual-range dogfights, they lacked the tactical repertoire their predecessors had developed. This recognition led directly to the establishment of Top Gun and similar training programs. The Navy Fighter Weapons School opened in 1969 specifically to address the deficiency in air combat maneuvering skills. Instructors, many of whom were Vietnam veterans like Cunningham, taught techniques that traced lineage back through Korea to World War II. The inverted dive and negative G maneuvers were part of that curriculum. Modern Top Gun instruction includes specific modules on negative G tactical applications. Instructors teach the physiological effects, proper execution technique, and tactical situations where the maneuver provides advantage. Students practice it repeatedly in training aircraft before attempting it during adversarial training missions. The goal is building muscle memory and physiological tolerance so the technique becomes available under combat stress. The training also understands why the technique works. Modern fighter pilots need to comprehend opponent decision-making, missile kinematics, and radar limitations. Negative G maneuvers aren't just about escaping enemy aircraft. They also break radar locks, complicate missile tracking solutions, and create opportunities for counterattacks. The same physical maneuver serves multiple tactical purposes depending on the specific threat situation. Contemporary air combat adds layers of complexity that World War II pilots never faced. Modern fighters carry missiles with sophisticated guidance systems that can track targets through maneuvers that would have been impossible to follow with guns alone. Helmet-mounted sights allow pilots to point weapons without positioning the entire aircraft. Sensor fusion provides 360-degree awareness that eliminates many historical blind spots. Yet the fundamental advantage of unexpected maneuvering persists. Missile guidance systems, sophisticated as they are, still require time to process new flight paths. A sudden negative G dive creates tracking problems for both the missile seeker head and the enemy pilot's situational awareness. That brief window of confusion, seconds at most, can be sufficient to break the kill chain. The F-35 Lightning II incorporates design features that facilitate negative G flight as a deliberate capability rather than emergency technique. The aircraft's fly-by-wire flight control system maintains aircraft stability through maneuvers that would be uncontrollable in mechanically controlled aircraft. Fuel systems ensure engine operation regardless of aircraft orientation. The pilot's ejection seat is designed to function safely during inverted flight, addressing a safety concern that limited earlier aircraft. These engineering improvements reflect how tactical requirements drive aircraft design. Engineers designing the F-35 knew that pilots would need to execute negative G maneuvers during combat. The aircraft was built from the beginning to support that requirement, rather than pilots adapting aircraft not designed for it, as happened with the P-38. The physiological challenges remain. F-35 pilots still experience redoubt during negative G flight. Blood still rushes to the head, vision still distorts. Modern flight suits and life support systems don't eliminate these effects, they're managed rather than prevented. Pilots train to function despite them, accepting temporary discomfort as the price for tactical advantage. This acceptance represents the culmination of 8 decades of accumulated experience. World War II pilots discovered through necessity that negative G flight was survivable. Korean War pilots confirmed it under different conditions. Vietnam pilots relearned it after institutional forgetting. Modern pilots incorporate it as standard operating procedure. The technique evolved from desperate improvisation to validated capability. The broader lesson applies beyond negative G maneuvers specifically. Combat generates tactical innovation continuously. Effective militaries capture that innovation, validate it, incorporate it into training, and pass it forward to subsequent generations. The process isn't always smooth. Institutional resistance, risk aversion, and forgetting create obstacles, but over time, genuinely effective techniques survive and spread. Richard Bong's split-second decision over the Solomon Islands in 1943 started a chain of tactical evolution that continues today. He couldn't have known that the maneuver he executed to save his own life would eventually influence how fifth-generation stealth fighters engage opponents 8 decades later. Yet that connection exists, directly and documentably, through the continuity of fighter pilot culture and institutional knowledge. Military historians often focus on equipment, strategy, and operational decisions made by senior leadership. These factors matter enormously, but tactical innovation at the operational level, generated by individuals facing immediate life-or-death decisions, shapes how wars are fought as much as any high-level strategy. The pilots who figure out what actually works in combat and survive to share that knowledge create effects that ripple forward through generations. The story of the inverted dive illustrates this dynamic perfectly. No admiral or general ordered its development. No engineering team designed aircraft specifically to support it, at least not initially. It emerged from combat necessity, proved effective through repeated use, spread through informal networks, eventually gained official recognition, and ultimately became foundational to modern fighter tactics. That progression, from battlefield improvisation to doctrinal standard, represents how military organizations actually learn and adapt. Official processes matter, but combat reality drives the evolution. Pilots facing Zeros in 1943 and pilots facing advanced threats today share fundamental challenges. Physical limitations, opponent capabilities, the need to survive and complete the mission. The solutions they develop reflect those constraints more than any specific technology or doctrine. The human element remains central. Fighter combat is ultimately decided by pilots making split-second decisions under extreme stress. Technology provides capabilities. Training builds skills. Tactics guide actions. But in the critical moment, the individual pilot must assess the situation, select the appropriate response, and execute it effectively. That human decision-making process connects Richard Bong and his P-38 to a contemporary F-35 pilot, despite all the technological changes between their eras. The inverted dive, as a specific technique, may eventually become obsolete. Future aircraft might maneuver in ways that make the distinction between positive and negative G flight irrelevant. Autonomous systems might handle aerial combat without human pilots experiencing physiological effects. The specific tactic isn't eternal, but the principle endures. When your opponent has an advantage in one dimension, shift to a dimension where you have advantage. When the enemy expects one type of maneuver, execute something unexpected. When temporary discomfort provides tactical benefit, accept the discomfort. These principles applied in 1943, in Korea, in Vietnam, in the Gulf Wars, and they'll apply in future conflicts regardless of technology. If this story moved you, we'd be honored if you'd like this video. Please tell us where you're watching from, your country and city. Did you know someone who served in the Pacific, Korea, or Vietnam? Perhaps a father, grandfather, or uncle who flew fighters? Share your memories below. These stories connect us across generations. The pilots who pioneered these tactics couldn't have imagined we'd still be discussing their innovations 80 years later. But their courage, ingenuity, and willingness to push beyond accepted limitations created knowledge that saves lives today. Thank you for watching. Thank you for remembering. These stories must not be forgotten.